inequalities. So less than or equal to. Well, remember, those always point left. Less than, left. And then greater than or equal to points to the right.
Let's make sure we understand inequalities. X greater than 6. That means X could be all values greater than 6. So like 7, 8, 9, or 6.2. Let's try to represent it on a number line. First, I want to plot a point at 6. But X can't be 6 if it's greater, so I'm going to plot an open circle there. I could draw it directly on my number line or floating above. Then greater than, that's like 7, 8, 6.2. That's headed in the right direction. So I'm going to fill in my number line to the right and draw an arrow to show it keeps going. How about you try X is less than or equal to 6? Notice, because it's equal to, we fill in our circle, and then less than, we point left. Let's name 3 solutions for these inequalities. One integer, one rational, and one irrational. One integer, X is greater than 6. Let's choose 7. One rational, fractional. Okay, X is greater than 6, so it could be 6.2 or 8.5 or 7.3. And one that's irrational, not fractional. So my decimal can't end or repeat. So like the square root of 82. I chose the square root of 82 because I know it's really close to the square root of 81, which is 9. I know where 9 is on my number line, and if the square root of 82 is just slightly bigger than square root of 81, I can plot it right here. Now try to name 3 solutions of those same types for X is less than or equal to 6. Check out my solutions. Yours are probably different. Remember, inequalities have an infinite number of solutions.
Now, you've probably always been told to flip the inequality if you multiply or divide by a negative number. But why? Well, let's start with the true statement. 7 is greater than 3. Now I'm going to multiply both sides by -1. So now I have -7 is greater than -3. That's not true. -7 actually has a smaller value than -3. So here we go. We've got to cross that out. And remember that if you do multiply or divide by a negative, you do need to switch the inequality. All right, let's practice solving inequalities. When we look at this first one, do you kind of want to distribute that 4? Because I do. But wait, there's 2 ways we can approach this problem. What happens if I undo the multiplication first? So divide out the 4 to start with. Well, it turns into a pretty nice number there. -20 divided by 4, -5. Great. Hey, wait a second. Do we have to switch the inequality? I have -5. No, because we divided by a +4. So there is no switching the inequality here. Last step, all we need to do is add 7, and we have our final answer. Notice the number line doesn't have any integers on it yet. So be sure and put a 0, couple tick marks, indicate that 2, and then of course it's an open circle because X is greater than 2, not greater than or equal, pointing to the right. This next problem, we have to distribute and simplify before we can start solving the inequality. So let's distribute -2/3. When we multiply -2/3 times 7, remember 7 is over a 1. So all I need to do is multiply the numerators and then multiply the denominators. Next, we need to combine like terms. We have -2/3 x minus 4x. Okay, we're going to have to add fractions. That means I need a common denominator. Well, -2/3, I need to change -4 into something equivalent with thirds in the denominator. So let's multiply the numerator 4 by 3 and the denominator by 3. That gives us -12/3. When I'm adding fractions, all I have to do is add the numerators, keep the denominator. So -2/3 plus -12/3 is -14/3 x. Now to isolate x, I need to go ahead and undo -14/3. So I'll add 14/3 to both sides. Once again, I'm going to need a common denominator to combine -2 plus 14/3. You could pause and try this. So we get 8/3. So now we have -14/3 x greater than or equal to 8/3. Well, we want it to be 1x, so I need to find a way to undo -14/3. Multiply by the reciprocal, -3/14 on both sides. Inverse property of multiplication. Now we just multiplied by a negative, so sometimes I like to stop everything right now, circle that inequality so that I remember to flip it even before I simplify the problem. Fortunately, we have 8/3 times negative 3/14, and the 3's divide out. So our final answer is x less than or equal to negative 4/7. Plot this on the number line.
All right, I know you're eyeing those parentheses like me, but think about it. What would the quickest way to solve this next inequality be? Divide out the 3. That would be so much faster. Then I'd be left with x plus 3 is greater than or equal to 2 plus x. I just have to move my variables to one side and isolate. Subtract x. Whoa. Then I get 3 is greater than or equal to 2. Is 3 greater than or equal to 2? Yeah, that's always true. So x is all real numbers. What happens in this next one? Solve. 4 is less than 4. That's never true. So no solution.
When we deal with two inequalities at the same time, that's a compound inequality. And it could be an or statement or an and statement. Now an and will shade in between two values, whereas an or shades out, or out. Always write an or statement as two separate inequalities, but you'll find out that an and statement can be written as one single linked inequality.
Check out the first compound inequality. It's an and statement. Let's take a moment, solve them both. A is less than 10 and A is less than negative 5. Oops, I forgot to flip my inequality when I multiplied by negative 5/3. Let's graph this on a number line. I'm going to plot 0, then count out to negative 5, and then count out to 10. Both are open circles because I have less than and greater than. A is less than 10, so that means I need to draw an arrow pointed left. I'm going to tweak that in a second. A is greater than negative 5, so now I have an arrow pointed to the right. So I have these two arrows pointed at each other. Well, we're going to make that into a bar. All of our values for A are in between that negative 5 and 10. So we want to make sure our solutions reflect that. So we're going to write A in between negative 5 and 10 for our solution set. Negative 5 is less than A is less than 10. And shades in between. This next example is also a linked inequality, so it must be an and compound inequality. I'm solving for x, so as I undo and add the 2, I have to add it to each section of my linked inequality. One is less than x is less than or equal to 9/5. See if you can plot that on your number line. Check your solution. Remember, and shades in, so they're always gonna look kind of like those little dumbbells on the graphs.
Now we see an or statement. Go ahead and solve each inequality, and we'll come back and talk about what it looks like on the number line. M less than negative 8. So open circle on negative 8 and shaded to the left. Or M greater than or equal to negative 5. So a closed circle on negative 5, greater than, so shaded to the right. Do you notice now that it's or out? There's no values in between. So that's why we never write it as a linked inequality. It wouldn't follow the number line very well. Always write an or statement as two separate inequalities. Do that next problem. Okay, so on this next one, m less than or equal to 7 or m greater than or equal to 7. So as we plot those two, closed circle, less than, points left, closed circle, greater than, points to the right, well, it ends up the entire number line. So this is m is all real numbers.
Number.
Dang it.
Infinitely
Infinitely many solutions.